Hello all, my name is Mantas, I'm from company Energy Advice, and today we have a seminar about the harmonic mitigation study with software EA-PSM. So before I start, please inform me whether you can hear my voice, so I will know whether connection is good and all technical things are correctly managed. Okay, I can see that some people are informing me that you can hear my voice, so which is good. And first, let me introduce myself. I am working in company Energy Advice. In this company, we are doing software EA-PSM. Software is actually is capable of calculating electric and hydraulic networks, and today I will show one module of the software, which is hydraulic calculations. So basically we have clients mostly in Europe. Also we have a branch office in India and in Kuwait. So in Energy Advice India you can also consult for getting the software. So we have clients in India as well that are using software for these calculations. Here's the map of our clients. Here's the introduction about the EA-PSM electric functionality. So basically it allows to do main calculations for electrical network design, maintenance, so basically for engineers who are working with electrical networks. So first of all, the main functionality here is load flows, and load flows analysis allows to estimate what are the current levels and voltages in the network. It allows to select equipment, cables, basically all the electrical network equipment. Then we have short circuit, which is needed for protection coordination and as well for equipment selection. And nowadays, because in electrical networks we have a lot of nonlinear loads which generate high frequency harmonics. High frequency harmonics actually have impact on all the electrical network equipment. Harmonics tend to overheat this equipment. So basically in our software we also added functionality for harmonic calculations, and we will work more on this today. Also we have arc flash, motor acceleration, cable ampacity, distance protection for high voltage networks, and many more functionalities actually regarding electrical network calculations. For more data you can always consult Energy Advice team. We will inform if we have functionality which is needed for your projects. Also, we suggest to participate in more detailed trainings. So here today we have 3 trainings, only 2 hours, but we also organize like advanced 16-hour trainings. So during these 16-hour trainings we cover all the electrical network topics, starting from equipment sizing, protection coordination in medium as well as in low voltage networks, also harmonics, arc flash, and basically all the functionalities that are included. So basically you can participate in these trainings to get more knowledge about how to do electrical network studies using software, how to make the report, and like that. So these trainings, however, are priced, and they cost 290 euros per user. But if you register till tomorrow, so you can also get a discount. And the users who already have EA-PSM software, so they can get a discount of 50%. So basically you can at least rent the software and get a discount for the trainings. So these prices will cover each other and you will be capable to use the software for several months and also will get the trainings. So for more details, please consult us using these either phone number, email address, or you can register directly in our website, which is www.energyadvice.lt, English site, so /en/training. So here would be my short introduction, and now let's go to technical discussion. I will present calculations on real time using software EA-PSM. You can also ask questions on real time, so if you see and something is not clear for you, so you can ask in YouTube chat. I will try to read your questions. Of course, there are quite a lot of people already connected, like 76 people, so if all of you will write some questions, I won't manage to cope with all those questions. So basically, I will try to find maybe those questions that might be more interesting for all people that are connected, so more technical questions. And commercial questions, I have colleagues that will help to answer, so they will answer directly to YouTube chat, so you can see already that EA-PSM is giving answers, where to find trainings, and other answers. So certificate, as we are European company, so actually certificate in your company, in your country might not be valid, but if it's in Europe, so yes, we can give also the certificate as well. So let's go now to the software calculation. So I will shut down the slides, won't need them anymore, and the topic, as I have mentioned, is about the harmonics today. So the first question that I would like to analyze, so basically what is harmonic in the electrical network, basically, and what problems harmonics create. So according to IEEE 519 standard, which is USA standard, but it is one of the most advanced and the most descriptive standard about the harmonics. So harmonic is higher than network frequency current created by nonlinear loads. So basically the main idea behind the harmonics is that these are currents, like you understand, I believe you understand what is current. So this is just the same current that you have in electrical network, but with a higher frequency. So example, in a normal network we can have like 50 hertz, like 60 hertz frequency, depends on what is the country and what standard frequency rating is used. So these harmonic currents, they have much greater frequency, and for example, if we are talking about fifth harmonic, so fifth harmonic will have 5 times greater frequency. This 5 times, for example, 50 and equal to 250 hertz. So this is the harmonic idea behind the harmonic. It's just a simple current, but with a greater frequency. So how these greater frequency currents appear in the electrical network? So basically they are created by nonlinear loads like variable frequency drives, also transformers when they are saturated, and other loads when we have saturated, for example, metal part, they can generate part of the harmonics. However, nowadays in electrical networks, most often source of the harmonics is variable frequency drive or inverter, for example, a solar power plant inverter. So this type of loads, they generate higher frequency currents, and of course we call them harmonics, as I mentioned earlier. So here are several examples of different harmonic levels measured with power analyzer. And in the first picture, where we have yellow and orange curves, so the orange one is showing current. So we can see that the current is having form of more than like some triangular form, yeah, not the sinusoid but triangular form, and the total harmonic distortion of this current is 18%. So with 18% we have something like this current, and the yellow curve is showing voltage. So voltage is quite sinusoidal, so it's not very distorted, and the total harmonic distortion of voltage is only 1.9%, so much smaller, and therefore voltage curve represents sinusoid more correctly. However, if we have, for example, a higher harmonic rating, like here we have 30%, so we can see that current is now even more far away from the sinusoid. Now we even have two peaks, yeah, that are created by higher frequency harmonics. So definitely, if our network current is having 50 Hz frequency, so if it starts to raise at 0, and after some time it again reaches 0, so here's the half the period. You can see that because of harmonic distortion, we have much more frequent deviation of the current, so which is represented by these two peaks. And here voltage is a little bit more also distorted, and the total harmonic distortion here is 2.1%. So a sinusoid is again a little bit distorted here. So now I'm talking about voltage harmonics as well. However, in my first sentence I said that the harmonics are basically currents. So how does voltage harmonics appears in the network? So the idea is this: when we have current harmonics in the network, so for example here's the single line diagram, or a simple single line diagram, so which I'll explain quickly. Here's the network, 10 kilovolts, so medium voltage network. Here is the transformer, which reduces voltage to 400 volts. And here we have some nonlinear loads, which are represented by these inverters. So these inverters, they generate current harmonics into the network. However, our cables, also transformer as well as network, they have impedance. And basically impedance creates a voltage drop. So when current is flowing through impedance, of course we have voltage drop. So if higher frequency current does flow through the impedance, so this creates also a higher frequency voltage drop, and that higher frequency voltage drop is considered as voltage harmonics. So basically current harmonics injected into the network from the inverters, they generate voltage harmonics, and those voltage harmonics are also can be measured and called as voltage harmonics as a separate part. So in electrical network we have current and voltage harmonics. Nonlinear loads, most commonly they generate current harmonics, but those current harmonics, when they are flowing through the network, they generate voltage harmonics as well. And how does current harmonics generate, what is the actually impedance of each element when current harmonics are flowing through them? So explained in this graph, in this picture. So if we have inductance, it can be a series reactor, it can be cable, so each element basically in electrical network has some inductance, and the inductance is measured by henries. So this is the measuring unit for the inductance. And actually when we calculate the impedance of the element, so we use this simple formula, which is 2 times P, which is a constant number, times frequency times inductance, and this gives us what is the impedance actually, or reactance, or whatever you call that part of the impedance is regarding to the inductance. So the idea is this, that if we have a higher frequency, so for example a higher frequency current is flowing through the inductance, so then reactance of that element is bigger. And in the right side here we have the graph which is showing frequency on x-axis, and we can see that definitely when the frequency is rising, also inductance of also the impedance of the element is also rising. So it means that elements like this, reactors, cables, they have bigger reactance for bigger frequency current. So if we have 5th harmonic, 7th harmonic, or even higher, so those harmonics will be less willing to flow through the cable or through the transformer than, for example, main current, which is 50 Hz, because 50 Hz has smaller frequency. So impedance is rising linearly with frequency. Also, we have different type of elements in electrical networks, which is capacitance. So these are capacitor power banks. It's also we can have series capacitors in high voltage networks especially. So here we have different story. Actually now reactance of the capacitor is equal to 1 divided by 2 times P times frequency and times capacitance. And we can see that now frequency is here in the lower part of the equation, which means that when we have bigger frequency, so reactance of the capacitor goes down for the bigger frequencies. And here is the graph which is representing basically the reactance of the capacitor for different frequencies. So basically if we have 50 Hz frequency, so we can see that capacitor has biggest reactance for this frequency. And basically if our frequency is getting smaller, so we can see that our reactance is also getting smaller in this way. So basically there are two main types of elements, and they react to harmonics different ways. In one way, when we have bigger frequencies, so impedance for the harmonic is bigger, and in another way, when we have bigger frequencies, so impedance goes smaller. So if you want to reduce harmonics, actually we want to have more of this, more of reactance. So basically harmonics won't be capable to flow through big impedance, and we will have smaller harmonics. Of course, this can also create high voltage losses, and this can create high voltage harmonics. So, but current harmonics might be reduced. And here with the capacitor, so capacitor actually shunts harmonics by consuming them. So a lot of harmonics normally are flowing through the capacitors in electrical network, and this creates problem. So what are the main problems in electrical networks regarding the harmonics? Main problems are actually overheating of the elements, especially of capacitors. So capacitor banks, because they consume a lot of harmonics, are more willing to overheat. Also, a lot of harmonics are flowing through the network transformers. So also overheating of the transformer, another problem that can appear. Harmonics, because they have bigger frequencies, so they create eddy currents in electrical network, and of course this can also saturate current transformers, and due to saturation, current transformers will give bad readings of data. For example, this can cause protection devices to trip without any fault in the network, so only due to a high level of the harmonics. So the main problem is overheating of the equipment, which causes a smaller time for the equipment, so we have to change equipment more frequently because of the overheating. So I see that you are very active today, and already asked quite a lot of questions, so let's give a moment to read through those questions. So Mr. Ganesh Kumar is asking, what is the effect of harmonics in the power system? So as I have mentioned, mainly is overheating. And another question by Mr. Kumar is, what is the allowable time for harmonics? So basically, harmonics, they create some temperature for equipment. So for example, when we have harmonics in the network, so this increases, for example, capacitor temperature. And the manufacturer specifies what is the longest time of the equipment, for example capacitor or transformer, to operate at certain temperatures. So we have to then check the different type of equipment. And for example, if we take capacitor, so it will be, let's say, some temperature like 80 degrees, 100 degrees, and at this temperature capacitor can operate, let's say, for 1 hour, and after that time capacitor will be damaged. So this is the limiting time. However, I would not recommend to concentrate on this limiting time, because we are willing to reduce harmonics so that equipment should not have to work with high harmonic level at no time. So basically no time is allowed for the equipment with a high harmonic rating, because it overheats the equipment and it reduces the lifespan of the equipment. So the higher the temperature, the shorter is the lifespan. So therefore we have to reduce harmonics, and the smaller the time, the better it is. So then we have a question by Mr. Thomas, and the question is, does high frequency harmonic current cause increase in temperature of the conductors? So of course it causes the increase on temperature, first of all because of those eddy current losses, as I have mentioned. So these are circulating currents which appear in the conductor, and this of course causes temperature increase. Then there is one more question by Mr. Kumar, and what are the nonlinear loads which causes harmonics? So as I have mentioned, in electrical networks, these are mainly variable frequency drives which are used for motor speed regulation. Then we have inverter, most commonly of solar power plants. So these inverters, they also generate nonlinear currents. During normal operations, other loads are linear. However, for example, transformer, if it is saturated, it can also generate high frequency harmonics. Also, one more type of loads is power sources. So all the computers, they have power sources, and basically those power sources, they also generate harmonics in the electrical network. Then we have a question from Mr. Bruno, and the question is, does your software have capability to represent both North and Thevenin equivalent harmonic sources? So basically in our software, according to IEEE 519, harmonic sources are represented as actually current sources, as I have mentioned in the beginning. So only one of these are only represented. So basically in software we only have current source representation of the harmonic sources, and this is the main type that we need in industry. So if you do studies regarding the industrial companies, low voltage networks, also medium voltage networks, so basically capability of our software is enough to calculate nonlinear loads. One more question from Mr. Kumar, and the question is, in what principles EA-PSM used to compute the power system studies? The idea is this, that when we create single line diagram, so based on this single line diagram which user draw, so here is the example of one of this diagram. inside of our software, we create matrices that represent this single line diagram. So location of buses, lines, which buses are connected by which lines, and then we use a matrix algebra based on the Newton-Raphson, also Raphson-Seidel method to calculate load flows. And these load flow calculations are used for 50 Hz and higher frequency calculations as well. These calculations are based on international standards like IEC as well as IEEE. So calculations can be checked based on these standards, and in our site you can also find validation cases where we do analysis of the calculations with our software and example results from the standards. One more question from Mr. Ajit, and is the question, is the software capable of determining the size of filter requirement to reduce harmonics? So basically yes, and today we do analysis on that. I will show how to select this kind of filter. One more question from Thomas. Is harmonic the main reason of transformer and capacitor explosion? So harmonic is the main reason of capacitor and transformer overheating, and overheating cause problems for insulation, and after the insulation wears out, so then we have short circuit. And this short circuit actually is the main reason for an explosion. So harmonic is the primary source in most cases, which overheats the equipment and causes problems to insulation. When insulation is damaged due to high temperatures, then we have short circuit which damages the equipment. And maybe last questions, then we'll go to our analysis, and other questions I will leave for later. So the question is from Mr. Pedro, and it asks, could you tell us something about capacitor explosion when there are harmonics? So actually this is a similar question to Mr. Thomas, and as I have mentioned, high level of harmonics overheats the capacitor. This damages insulation inside the capacitor, and then we have short circuit inside the capacitor. Short circuit usually has high current, which is actually the main cause of explosion of the capacitors. So here is a short introduction about the harmonics and answering to your questions. So now let's start off doing harmonic calculations in example which I have prepared, and we will check what are the results of the harmonics. So before that, I would like to introduce the network itself, and basically the network starts from a high voltage side. It's 110 kilovolt, and this is the voltage level which we have in our country. And this high voltage is reduced through 20 megavolt amps transformers to a medium voltage network which is 10 kilovolts. So this is the main idea about the network. Then we have distribution network which is actually constructed of different type of lines. So we have overhead lines, for example 3 kilometers overhead line here. Also we have cables 800 meters, 1.5 kilometer, and different equipment connected. For example, here we have 2 megawatt solar power plant, which is also harmonic source. Here we have a powerful non-linear load, which could be again some kind of inverter. Inside the software, both of these type of loads, as I have mentioned, are represented as current sources for the harmonics, which creates a higher frequency deviation. So now we have also transformer, one more transformer which reduces voltage from 10 kilovolts, so from distribution network voltage level to 400 volts. To low voltage level side, and this transformer is 1 megawatt. Transformer name is transformer 2. So basically here we have now a low voltage network side, and basically in low voltage network side, as normally we have cables, again some non-linear loads. It can be variable frequency drive, for example. We have some amount of linear loads, so these are represented by these triangular elements connected in the network. And we have also capacitors. Here is the capacitor bank constructed of 25, 50, 100 and 100 kilowatt capacitors. However, these capacitor banks are now disconnected because these lines here represented in red color in our software means that these lines are disconnected. I can use my keyboard to connect them. So I just highlight the cable, push Q letter on the keyboard, and it automatically connects back on. So when it's in black color, it's connected. When it's in red color, it's disconnected. So first calculation that I would like to do is what is the voltage and current in the network of 50 Hz current, 50 Hz frequency value. So I will calculate power flows. I can use my keyboard as well to do the calculations and to get the result. So I can see that without the capacitor banks, 50 Hz current is 36.5 amps in the high voltage side, in medium voltage side in this case, and 932 amps in low voltage side. Power factor is 0.94 and the power flow is 657 kilovolt amps. So here is the calculation results of 50 Hz current. Now let's calculate then what are the harmonic flows. So I have calculation harmonic flows here in the software, and this will give me information first of all about the harmonic currents in the transformer. I can move my mouse cursor on the transformer winding, and this will give me information about what are the currents of each harmonic, which is estimated for the calculations. So I can see that fifth harmonic is equal to 78 almost 0.5 amps, and this is equal to 8.4%. And also you can see other harmonics like 7th, 11th, and all the others up to 25th. And also in the last column represents a total harmonic distortion, and this value is again quite big, and it is equal to 10.3 almost percent if compared to nominal current. So this histogram, which is represented by the software, also has one more type of information. So these are red and green lines. So if the line is represented by red color, so like in case of fifth and harmonic and total harmonic distortion, so it means that this particular harmonic is exceeding permissible limit based on IEEE 519 standard. So I can see that fifth harmonic is exceeding the limit by just a little bit. Then we have some green lines, and those green lines are representing histograms that are not exceeding permissible limit. You can see also what is the margin left. So now in this transformer only fifth harmonic is exceeding the permissible limit for the current. When I move my mouse cursor on the bus bar, I get a similar histogram, however with different units. Now I have information about the voltage harmonics, and I can see that in case of voltage harmonics, none of them exceeds the permissible limit. So all the lines are represented in green color. So this is one way to analyze the network after harmonic calculations. I can just simply move my mouse cursor on any cable, any element in the network, and this gives me information about the harmonic currents in that particular location. I can also use Harmonic Summary for this. So in Harmonic Summary, there is capability to actually open a harmonic chart. So for example, I have a low voltage section 2. So low voltage section 2 in the summary is here, and I can push the chart to open it, and this will give me the chart. I can make the better view away by making it bigger. So here, when I move my mouse cursor on each of these green lines, I also see what is the permissible limit. So like in fifth harmonic, the permissible limit is 6%, and now I have about 2%. If I move my mouse cursor on the harmonic itself, so software will give me information about what is the frequency of that harmonic, what is active and reactive part of that harmonic voltage or current. So basically, I can analyze harmonic results also from the summary of the calculation which I have just made. So what I would like to do now, I would like to save harmonic results, and then I will connect capacitors to the network to compare harmonic results with in the network without the capacitors and with the capacitors connected. So to do that, I will open Project Panel. So inside our software we have tool which allows to create harmonic reports. So basically it is possible to add harmonic histograms directly into the report using only our software. So you even don't need Word or other text processing tool to make the report itself. So I can add additional pages for my harmonic report, and I can add harmonic calculation results, let's say from low voltage section 2. So here I will have voltage harmonic results, and maybe I can add from my transformer. So again, harmonic transformer 2, 10 kilovolts to 0.4, and I'll take winding 2 to get low voltage side currents. So here are my harmonic calculation results after the first calculation without no capacitors. Later on we will be capable to compare these results when I will connect the capacitors to the network. So maybe I will change the network mode. Say mode 1 is with capacitors connected. As you can see, network is all the same, just the capacitor line is connected. So what I would like to do, first of all, I would like to check also normal frequency current. The goal for me is to reduce reactive power so that I will have compensated network mode. So when I move my mouse cursor on the power rating, I can see that my current is a little bit overcompensated. So the active power is 620 kilowatt and the reactive power is minus 67. So actually I can reduce the capacitive power a little bit. I will disconnect this capacitor and maybe this capacitor to reduce overcompensation, and I will calculate the power flow again. So when I disconnected some of the capacitors, I can see that now my power factor became better. Now it is equal to 1, and I have a little bit of undercompensation, which is equal to 11 kilowatt. But actually 11 kilowatt is not a big undercompensation, so I can leave the network as it is. And now I am capable to calculate the harmonic because this is the expected rating of the network, expected mode of the network with capacitors connected. So I will calculate harmonics one more time, get the harmonic results, And I can see that after calculations are finished, so I have quite a different view. So when I move my mouse cursor on the transformer winding, I can see that now quite a few harmonics are exceeding the permissible limit, and those harmonics that exceeding the permissible limit are 5th, 7th, and also 11th harmonic. Well, as well as THD, so total harmonic distortion value is also exceeded. When I move my mouse cursor on the bus bar, I can see that one of the harmonics now is also exceeding the permissible limit, and this is the 7th harmonic, which is exceeding that permissible limit. Of course, this is not good. This is causing problems to the electrical network equipment. When we have to start harmonic problems, I have one more slide prepared. So then now as we have made the calculations, and for example your client or yourself, you are interested when you need to reduce harmonics, when what is the level of harmonics that is actually bad. So I would say in this way. First of all, you have to check what are the current and voltage harmonics, and if those current or voltage harmonics exceeding the permissible limit, so this is bad, and actually you have to try to reduce problems related to the harmonics by, for example, applying harmonic filters. One more possible reason is that you have a harmonic resonance in the network. And now you have saw yourself that without the harmonics, without the capacitors connected, harmonic currents were much smaller. But as soon as I connected the capacitor bank, so the harmonics went very high, and this is the idea behind the resonance. So when we connect capacitors, this can cause resonance, and resonance is increase of the harmonics. And if you have this kind of process in your electrical network, so then you have to take actions to try and to reduce the harmonics. So resonance in the electrical network is not allowed. One more, for example, reason why you have to take actions to reduce the harmonics, so is if your transformers are highly loaded. So for example, if you have a transformer in the electrical network, which is usually quite overloaded. So for example, normally working at 80% loading or even higher. So of course you have to check what are the level of harmonics, because very loaded transformer will already work at a high temperature, and if you will have more harmonics, so this can exceed the permissible temperature of the transformer. So if you have highly loaded transformers, again you have to check what are the levels of the harmonics in your network, and if they are high, you have to reduce based on the permissible limits. So now one more possible reason why you have to change the way harmonics appear in the network, so is problems with the capacitor banks. So if you have to change capacitor banks very frequently, so again this is a problem, and you have to take actions to reduce the harmonics. So what I would like to do for my comparison, I will open the project panel again, and I would like to add now harmonics from the mode with capacitor. So maybe I'll add them here. So let's go to chart, harmonics. I will add harmonics from mode 1 and low voltage section 2. So now we can maybe a little bit change the way these charts are, the weight charts are put on the page, and this will allow us to compare the harmonic values. So basically, let me zoom in a little bit. So without the capacitor, which is represented by this upper chart, my harmonic, actually total harmonic distortion in case of voltage harmonics was 3.8%. When I connected the capacitors, my total harmonic distortion increased by 6.6%. What also happened is that 7 harmonic exceeded the permissible limit of the harmonics, and now it is 5.3%. Before it was only 2.1%. So actually we can say that the resonance is for our 7th harmonic. Let's check what happened with the current harmonics as well. I will add one more page. So the first chart is without the capacitors. Let's add one more chart with capacitors connected. So we can see that in case of harmonics, current increase was even bigger. And for example, when we connected the capacitors, current harmonics increased from 10% to 23.7%, so more than 2 times. And those harmonics that increased the most was 7 harmonic, also 5th harmonic, and also 11 harmonic increased by more than 2 times. So this is the resonance, and we have resonance especially for 7th harmonic. So this is not good, and actually we have to take actions to reduce those harmonics in the electrical network. I saw that there are people who are asking questions how we calculate the harmonics, so how we provide data regarding the harmonic currents. So let me open you the inverter. In our software, user is capable to specify nonlinear load in this way. So you have to specify inverter power. First of all, what is the active and also what is the reactive current of the load, and also you have to specify what are the harmonics and what is the rating, what is the value of the harmonics that are generated by this load. So now I have opened this inverter and I have this harmonic spectrum provided here. I can see that, for example, in this harmonic spectrum it is specified that this nonlinear load is not generating no 2nd harmonic, no 3rd harmonic, no 4th harmonic, but it is generating 5th harmonic, and the generated current is equal to 17.5% from the nominal current. So quite a huge current generated from the inverter. Then we have no 6th harmonic. However, this inverter is generating 7 harmonic, and this 7 harmonic is equal to 11.1. So already based on this harmonic spectrum, you can understand that this is a 6 poles inverter. So 6 poles inverter, it generates the harmonics of 5th, 7th. These are the main frequencies. Also it generates higher frequencies like 11th, 13th frequencies, but they are smaller, so basically they have smaller value. For example, for comparison, if 5th harmonic is 17.5, so 11th harmonic is only 4.5, so much smaller. So in industrial networks, most problems are with 5th and also with 7th harmonics. Except, for example, if you have resonance for some higher frequency of the harmonic. So here is the idea behind the harmonics. Also, I saw one question regarding 3rd harmonics. In electrical networks, we also have power sources like a computer power source or lightning equipment power source. So these power sources, they are 4 poles inverters. Basically, they change current from alternating to direct, so they equalize the current. And these type of power sources, they also inject 3rd harmonics into the network. So basically, software is also capable of calculating these harmonics. I just have to specify what is the level of the 3rd harmonic, and then I can make the calculations regarding that particular harmonic. However, during today's trainings, I won't concentrate more on this harmonic, which is more common for administrative buildings, like also shopping malls. I will concentrate more on harmonics that exist in industrial networks, like production plants and also distribution networks. Because those third harmonics, they are very small in distribution networks. In most cases, they do not exist in the distribution networks at all. So one more example, and after that I will also check your questions. So basically we can see that when we connect capacitors to the network, this is not good because harmonics increase significantly. Also our capacitors, I can move my mouse cursor on the capacitors as well, highly loaded with the harmonics. I can see that more than 50% of current is basically nonlinear, so basically it's harmonics, and only half of that is normal frequency, which is not good. It means that capacitor will overheat, and after some time it can explode and definitely will be damaged. So this kind of configuration in this network is not recommended. I can disconnect capacitors and also line which is going to the capacitors. So what we can do in this kind of network, so how we can reduce the harmonics. So one possible way of reducing the harmonics is by reducing resonance, which was caused by the capacitors. And for resonance reduction, we can use so-called detuned harmonic filters. So here is the example of several detuned harmonic filters. Again, we have to maintain the same reactive power. So detuned harmonic filter, it does two things. One thing is it provides reactive power to the electrical network. As we can see, the tuned harmonic filter has capacitor and also reactor. So it provides reactive power. And another thing it does, it reduces impedance. It makes actually impedance not capacitive, but inductive of this element. So if we connect only capacitor, so impedance of the capacitor is capacitive. If we connect capacitor through a high inductor, so then impedance of this unit becomes inductive, and basically it does not allow for resonance to appear. So the idea behind this is to create enough impedance in front of the capacitor to reduce harmonic resonance. So now reactor here is selected to be 6%. Normally you have several steps of the capacitor of the reactors, which are provided by the distributors of the equipment. So now I selected one of the smallest possible sizes. There you can buy also like 3%, 7%, 11%, but now I selected 6% impedance. And I will calculate harmonics again, harmonic calculations, with these capacitors connected. So I can see directly that when capacitors are connected, harmonic currents are reduced quite significantly. Basically, none of the current harmonics exceeds the permissible limit. Also, total harmonic distortion is within the limit, as well as basically our normal, like voltage harmonics, are also all within the limits. So let's check in the summary of the harmonics protection. So harmonic summary, current harmonics, let's say in transformer here maybe. There is no load line. So transformer 10 kilovolts, I will increase the size. So I would like to check current harmonics in basically this this transformer winding. I will open the current harmonics. Let's go to protection panel to check what was the harmonics before I connected my tuned harmonic filters. So here are two histograms of the same line. So basically in both cases I have transformer 2, winding 2, and in the right side you can see how the harmonic currents looked like without the tuned filter. You can see that 5th, 7th and 11th harmonics were all exceeding the permissible limit. Also total harmonic distortion was exceeding the permissible limit. As soon as I connected the filter, all of those harmonics went down, and actually none of those harmonics exceeded the permissible limit. So total harmonic distortion is now only 6%. Before that, the harmonic distortion was 23.7%. So you have a huge reduction of the harmonics. So these are the main type of filters that are used in industry, the tuned harmonic filters. To create this filter, you actually only need to connect some impedance in front of the capacitor. So you have to buy the inductor, the compensation coil, like reactor coil, which you can connect in front of the capacitor. This will create impedance, and basically it will reduce the harmonics. How to select what size of the impedance you should have? So you can do this using the software. For example, I can select smaller impedance values. Instead of 6%, I will specify 2%, which is actually giving me the smaller impedance value, and I can check whether this kind of frequency is enough for my harmonic mitigation. I can see that with 2% impedance, still some of the harmonics exceed the permissible limit, which is not good. And what is the current flowing through the capacitor? It is 83%, for example, in this capacitor, which is not good at all. So it means that this capacitor is very overloaded with the harmonics. So of course 2% is not enough for us. So our goal is to select frequency, to select impedance, which will be enough to reduce harmonic currents within the permissible limits. So we have to reduce them so that all the harmonics are inside the permissible limits, and also harmonic currents that are flowing through the capacitors should not exceed the permissible limit by the manufacturer. So now instead of like 90%, 80%, which I had before, I have only 14.5%. This is a major reduction. So the impedance that I have selected, which is 94.6 milliohms, or if I show this in per unit system, so it's 6%. So it's equivalent to 94.6 for this particular 100 kilovolt amp reactor. So with the software you can very easily select what is the impedance that you need for the filter to avoid the harmonic resonance in the electrical network. So you can just simply enter one value, another value. You can make calculations very quickly and get the results, and according to that you can select what is the frequency that you need to actually solve the harmonic problems. So this is the idea behind the tuned filters. Why these filters are most commonly used? So because they are most cheapest alternative, you only need the reactor in front of the capacitor. It allows to reduce harmonics that are flowing through the capacitor. So when we had the resonance, harmonics flowing through the capacitor were more than 50%. And now with these filters connected, flowing harmonics are only 14%, so much smaller. So we have to select a filter which will reduce those harmonics. Also, these filters are not very much affected by loads in the distribution network. For example, now we have current harmonic distortion equivalent to 14.5%, And for example, if in distribution network someone will increase the power, for example, from 2 megawatt to 3 megawatt of this inverter, and if we will recalculate the harmonics, we will get that harmonic currents increased, but not too much, like only 2%. So the idea is that these filters, they are not very sensitive to like things that are going on the distribution network. So therefore they are most commonly used, and like the most common alternative in industrial network that you can recommend for your clients using EA-PSM software. So the next example will be about the tuned harmonic filter. So these were the tuned filters. Now I will explain also what are tuned harmonic filters. However, before that, let's try to calculate a few questions. I can see that you have provided quite a lot of questions while I was giving the presentation. And let's start from Mr. Osman. And the question of Mr. Osman was, is RMS voltage value with harmonics always higher than the fundamental voltage value? Actually, not too much. Normally, RMS value is not very much affected. Maybe if we'll consider very sensitive measuring equipment, so we will find this increase in RMS value, but it's not very much affected by higher frequency harmonics. Also, the reason behind this is that those higher frequency voltage harmonics are usually not that big. For example, if we'll take this bus bar, so we can see that first harmonic is 230 volts. This is the normal 50 frequency harmonic, and other harmonics are all smaller than like 4 volts, 3 volts, so very small, and those small harmonics, they not affect the RMS value too much. Then we have one more question. Will harmonics have magnetizing currents? So basically harmonics, they create two types of currents. One is eddy currents that are creating losses inside the core of the transformer, and another type of current is stray current, and these stray currents, they create again losses in all the metal parts that are around the transformer core. So it can be for example transformer walls, transformer cooling coils, and all these kind of metal things. So they are affected by stray currents. So harmonics create these type of currents. Then I have a question from Marcelo. He is asking whether we have libraries in the software. So yes, we have libraries for power cables, for relays, and all the other equipment. So in modeling chart, we can see what are the possible libraries. So cable, wire, tower, transformer, generators, motors, here circuit breakers, overload protection, and different type of protections in case of electrical network. And the other part was whether we can provide software for macOS. So basically now we provide software only to Windows. So the short answer to this question would be that it's only on Windows now. Then let's see other questions. The question from Mr. Roshan, which circuits are more sensitive to the harmonics, power circuits or communication circuits? So basically communication circuits can be protected from the harmonics by using shields, metal sheets that are grounded. and then they are not that sensitive to harmonics. Also, frequency of the harmonics are not that big. For communication circuits, maybe higher frequencies are more can more affect them. But of course, if you have cable ladders, and on those cable ladders you have power cables that are not protected by shields, and also have communication circuits, so of course communication circuits will be affected. In case of power circuits, so power circuits are quite affected quite a lot, especially, as I have mentioned, capacitors and transformers. Then there was a question from Mr. Karima, how to identify the harmonics using EA-PSM. So basically we have to calculate the harmonics, and this will give us information about the harmonic levels. So we have done this several times today, so just simply by checking the values of the harmonics. Then there was one question from Mr. Saleh, and the question was the software considers IEC 61000 summation law to add up the harmonic currents from different sources? So actually that summation law is needed only when you don't have software and you do hand calculations. But when you have software, so you don't have to use that summation law. And for example, here I have one more harmonic source, here I have two more harmonic sources, and when I calculate the harmonics using the software, so software automatically does the summation of the harmonics inside this line. So basically you don't have to use those summation laws with the software, because they are considered by calculating power flows and using power flows algorithms. Those summation laws are only needed when you do hand calculations. So software allows to analyze networks much more easily than with the hand calculations. Then there was one more question which was provided by Bruno. So he is saying that IEC standards applies to most countries in European Union, especially in wind energy. And this IEC, I believe, according to Bruno, used 7 in representation of the generators. So the idea is this, that the IEC standard might apply to European countries, but if we take practical analysis of the network, so in industrial networks, most of the loads are current harmonic sources. So the calculation algorithm to analyze current harmonics is enough to analyze the industrial networks. In other case, like if we have wind turbines, which might be like voltage harmonic sources, so then yes, we might need other type of the calculation. But again, if you have measurements of what are the currents created by the wind turbine, so you can use those calculations to actually do also wind turbine calculations in the software as well. Then there was one question from Mohammed, and the question was, can LED, so light emitting diode, cause leading power factor? So in most cases they don't cause leading power factor. They have, of course, power sources, and those power sources in most cases have lagging power factor, so like reactive power factor. But if a manufacturer adds a very powerful capacitor in the power source, so of course leading is also possible. Question from Kumar: is it possible to design active harmonic filters? So yes, active harmonic filters can be also designed, and I will be capable to show this as well. One more question from Mr. Marcelo. And in the industry, it is important to use software that comply with international standards. So what standard does your software comply with? So depends on what calculations you are looking for. So in case of short circuit calculations, we comply with IEC standard based, for example, of arc flash calculations. So arc flash calculations have IEEE standard. We don't have any standard in Europe which represents how to do those calculations. Then if we take power flow calculations, so there is no standard for power flow calculations. There are only standard test cases that we can check and say that our software is doing right calculation. So IEC or IEEE in this case is not important. And the same thing is with the harmonics. Basically, for calculating the harmonics, most comprehensive standard is IEEE 519. So it describes how to evaluate nonlinear loads, how to evaluate cables, transformers, and other equipment. Other standards, like in Europe, they do not describe how to do calculations. They only provide permissible limits. So these permissible limits are evaluated in our software. So basically, you can compare permissible limits from IEEE as well as IEC standards. But calculations are only provided in one standard that we use in our software. Then there was question with Kumar why capacitors are installed with shunt reactors. So of course they are installed in order for reducing resonance conditions. And of course software evaluates harmonics by doing calculations based on IEEE 519 standard. But as I have mentioned, the main calculation behind this harmonic flow is simple power flow, and power flow does not have standards which specifies how to perform. There are methods like Newton-Raphson method, how to perform power flow calculation, or Gauss-Seidel method, so different methods, but these are not covered by any standards. One more question from Mr. Zhang. Can this harmonic showing an individual element be set with different harmonic orders in the software? So basically you can set the harmonics only in those sources and those loads that generate harmonics. You cannot set the harmonics in linear loads because linear loads they are not generating them. And therefore, when you set harmonics in non-linear loads, so then software automatically calculates what are the harmonics in non-linear loads as well, and what are the harmonics in all the other network elements. So this is the main idea behind the software calculations. Now, let's go to one more example, and before answering the questions, I worked with the tuned harmonic filters, so to avoid harmonic resonance. For example, we want to reduce harmonics even more. So with the tuned harmonic filters, we reached a harmonic value of 6%. But if, for example, our goal is to reach even smaller harmonics. So different type of filters that you can use is tuned harmonic filter. We can connect this filter to the network. So tuned harmonic filter is actually a very similar element to the tuned harmonic filter, except that it's selected in a different way. So when I open the tuned harmonic filter, so first of all, software asks me to select filter type, and there are different types for tuned harmonic filter. For example, it can be C delta L star connected filter. So this filter has inductances connected to the ends of capacitors connected in delta connection. Here is the most commonly used filter type in industry. Then you can have, for example, double tuned filters, which can reduce the harmonics at 2 frequencies, not 1 but even 2 frequencies. And you can have C-type filters, which are used for higher frequency levels and to reduce higher frequency harmonics. So different filters for different applications. Then we also have to choose what harmonic order will be reduced. So for this filter we have to reduce harmonic order, and basically for example, I would like to select fifth harmonic order. So my goal is to reduce fifth harmonics in the network. And we have to specify what is the power of the filter. The more powerful the filter, the more harmonics it will be capable to consume. So in this case, for example, I will specify 100 kilowatt, which is the power of the reactive filter, and software will automatically calculate what is the inductance needed for this filter. And in this case, inductance is equal to 203 millihenries, which is the inductance value. Software also calculates how does impedance chart look of this filter. So basically we can see that when frequency is smaller than 250, so fifth harmonic is equivalent to 250 frequency. So basically when I have smaller frequencies, my filter works as a capacitor. So because the impedance of this filter is reducing. So if you go to the slide that I showed you previously, you can see that these curves are similar. Yeah, so here I have reducing impedance, here impedance is also reducing. So the higher the frequency, the smaller is the impedance. However, when I reach fifth harmonic, so impedance of this filter for the fifth harmonic is very small and almost equal to 0. Yeah, it depends on the resistance only. If the resistance, let's say, is 0.1 ohm, so also the impedance will be 0.1 ohm. So the smaller is the resistance, the better actually is the filter, and the more harmonics will be mitigated, consumed. And if we go to frequencies that are higher than fifth, let's say frequency equal to 500 Hertz, you can see that this filter has inductive impedance for this filter. For this harmonic means that if we have 500 Hertz harmonic, so this filter will work as simple inductor, a simple linear load for this particular harmonic. So our filter will try to mitigate harmonics by consuming them in the electrical network. So I connected the filter here. Now let's try to calculate the harmonics, and before we connected the filter, the harmonic values was over 6%. Now with the filter connected, I can see that harmonics are reduced and they are equal to 4.8%. So let's try to disconnect the filter one more time and repeat the calculations. Yeah, so now it's 6.1% when the filter is connected. So harmonics go down to 4.8%. So it's good. However, there are some problems regarding this tuned filter, and one of the major problems is that these tuned filters are very sensitive to what is happening in distribution network. For example, if in distribution network someone will connect a more powerful load, say instead of 2 megawatt, let's connect 4 megawatt load. So this filter will overload. So now when we have 72.2% harmonic current flowing through this filter, this is a very high harmonic content. However, if someone in distribution network will increase the load, we can see that harmonic distortion will reach even 90%. So this is a very sensitive reaction to what is happening in the electrical network, and this 90% can overload the passive filter. So if we'll do design of a tuned harmonic filter, you have to evaluate what is the current, what is the existing voltage harmonic value, and in the distribution network you have to represent situation of the existing voltage harmonic in this point where your transformer is connected. So when you have voltage harmonic evaluated, you can connect a passive filter and you can check whether this passive filter will not overload. So this is a more advanced topic which we analyze during EA-PSM Academy. So how to solve this problem? Actually, in order to avoid this filter from overloading, we can use this filter, and most commonly this filter is used only for single nonlinear load harmonics reduction. So we have this inverter connected here, and for example we only want to reduce harmonics of this inverter. So what we have to do, first we have to add harmonics gate. Harmonics gate is inductor which does not allow harmonics to enter from the distribution network into the analyzed busbar. So here is the harmonic gate. I will enter, let's say, a harmonic gate. Power of the harmonic gate should be big enough to transfer power from inverter and also short circuit voltage, so percentage impedance. Let's say I will select 4%, 3 kilowatt. These are losses of the harmonic gate, and when I have harmonic gate connected, I can then reconnect my filter here to the inverter connection point. So here I now have tuned the harmonic filter for single nonlinear load harmonics reduction, and I have this harmonic gate which won't allow harmonics to enter into the network. Most of the harmonics from the inverter will go to this passive harmonic filter, and also the good thing is that this harmonic gate won't allow harmonics to enter from the network inside this bus 29, and this will allow to avoid tuned filter overloading. So now with this configuration, let's try to calculate what are the harmonics in the network. You remember that before I did this harmonic gate thing, so passive filter was loaded with the harmonics equal to 99, like a 90%, so very high harmonic level. When I added this harmonic gate, so I can see that my passive filter is not very overloaded with the harmonics. It's like only 66%. So basically harmonics from the electrical network are not entering here inside this bus 29 where my passive filter and inverter is connected. So tuned filters should be used in most cases for single nonlinear loads and together with the harmonic gate, which allows to avoid the overloading of the filter. So here is how you can actually size a tuned harmonic filter. So now let's check what are the harmonic levels in the network. So I can see that harmonics are only 3.5%. Here are current harmonics, and let's check what were the harmonics before we started our study. So harmonics before was 23.7%. So from 23.7% we reduce harmonics to only 3.5% by using like these filters with the tuned these capacitors with the tuned filters and one tuned filter. Of course, this tuned filter also generates reactive power, so in order to avoid the overcompensation of reactive power, I will disconnect one of the filter here. So I will have 100 kilowatt here and also 100 kilowatt here. These two filters will be enough to reduce harmonics, and this will also give me even a little bit smaller harmonic values. So basically with these two type of filters, we reduce harmonics quite significantly. So one more type of filter that you can use inside our software, and also I saw that there was question regarding this particular filter, is active filter. So active filter works, there are actually several types of different active filters and how they work in electrical networks, but one of the most advanced types is that active filter is measuring harmonic level on the real-time basis. It checks what are the harmonic, for example, currents flowing in this transformer, and this filter injects into the network also higher frequency currents, but with the opposite phase angle. When you inject into electrical network current with an opposite phase angle, what happens basically, your currents mitigate each other, so they like sum, and because phase angles are opposite, so they sum to zero, so they mitigate each other. So this is one of the possible ways how active filter is working. In order to select the active filter, I have to specify what element this active filter is measuring, and I will specify that this filter is measuring transformer 2, winding 2, and I will specify the power for this filter, let's say 20 amps. Sometimes active filter can work bad with the tuned and the tuned filters, so we will check here in the software whether these filters will not cause problems to each other. So now let's do the calculations of harmonics. I can see that after I selected the filter, my harmonic currents were reduced even more. I have only 2%, and probably if I make my filter even more powerful, so harmonic currents actually can be reduced even more at 1.3%. So basically we can see that harmonic currents in my transformer are reducing. However, we can see also that voltage harmonics in busbar has a little bit exceeded. So let's go back to 20 amps. So here I have 2.1%, and when I have harmonic calculations, so it's 2%. So a smaller filter gives, in this case, smaller voltage harmonics. The idea is this, that as I have mentioned, the active filter is injecting harmonics into the network as well, however with an opposite frequency. So when we calculate the total sum of all the harmonics from all the harmonic sources, also what are the harmonics going to the loads, and what are the harmonics going to the capacitors, we see that with the filter harmonics, voltage harmonics just a little bit increased, but by just a very small amount. So, but in other ways, so this filter helps to mitigate harmonics and reach very small harmonic values. So if I'll disconnect passive filter, let's say I will leave the tune harmonic filter, and let's calculate harmonics. Without the passive filter, harmonics are 5.5%, and let's say I will add more powerful active filter to reach 1.7%. So this is the way active filter is selected. You just simply have to make sure which part of the network is measured, and you have to select power of the active filter. Like what is the maximum current this filter injects into the network. Okay, so let's check some more questions by you, and I don't remember exactly where I finished last time. So basically there are questions like asking can I show the harmonic plot with capacitors and without the capacitors. So we did this in the beginning of the seminar, and all the seminar will be recorded, and you can rewatch it in YouTube. Actually, so basically you can check those plots with the capacitors and without them. Then there is question what is the permissible limit of the harmonics. So it depends on the standard you are looking at. So you can go to the Harmonics Summary and check what are the limits used in our software. So like for fifth harmonic 4%, for seventh harmonic 4%, and so on. However, these limits, they also depends on how powerful is your network, and network power is described by short circuit current. So the bigger is the short circuit current, the bigger is permissible limit. So in our software, in order to determine harmonic limit, we also do short circuit calculation to estimate how powerful is the network, and according to that we decide what is the permissible limit based on the standard. However, the idea is that you don't have to do all these things manually. Software does the calculations automatically. Then there is question by Marcelo, and the question is, until what harmonic does it calculate? So now in software we allow to provide harmonics up to 50, and then it says that in the UK standard we have a new standard that says and has requirement to calculate harmonics up to 100. So based on IEEE 519 standard, so this requirement is still not valid. If in UK you have this kind of requirement, so it depends for what reasons you have this requirement and why you need to calculate this. Higher frequency harmonics, like 100 frequency, like 100, it would be like 5000 hertz harmonics. They are more affecting like communication lines, and in our software, because we do calculations of power networks, so these very high frequency harmonics are not that important. So for power network analysis in IEEE 519 standard, still we don't have this requirement. But if you want to calculate high frequency harmonics with our software in power network, so we can add additional number of harmonics that can be specified, so it's not a problem. So now let's talk about other questions that we have, and how often we need to exercise capacitor banks, how to know this time period depending on the kilowatt of capacitor bank. So the question probably was how often we have to check capacitor banks. So actually you never know how fast equipment will deteriorate. So you can check from time to time, but the idea is that usually energy bills show that your capacitors are not having enough power. So just based on energy bills, you check if the bills and reactive power consumption is not too big, so that's okay. If power consumption is very big, so then you have to take some action to reduce it. Okay, so there are quite a lot of different questions. I see that some questions are repeating. There are some questions I see regarding the eddy current losses. So one more thing that I would like to show inside the software, so is how eddy current losses affect eddy currents affect losses in the electrical network. So here is the simple formula, which is actually the power losses in any equipment. It can be a transformer, it can be a cable line. So any equipment you can imagine in the electrical network. So is the losses in that particular equipment represented by P letter in kilowatts. So how those losses are constructed when we have harmonics in the network. So first of all, there are some losses in, for example, cable, even if we have DC current flowing. So this DC current losses depends on resistance of the cable, and they are not avoidable, and they do not depend on the harmonic level too much. So total losses are equal to DC losses, and here we have some more interesting losses that depends on the harmonics. So here is the factor F, which represents harmonic level in the network. The higher is the F rating, the more harmonics we have in the network. And we can multiply factor F by power losses in electrical network without the harmonic in order to get losses with the harmonic. So software does allow to calculate this factor F. We have one more factor FHL slash SCR, which is a factor for stray losses. So if I open summary table, let's go to Harmonic Summary, and if I take branches, let's say any cable or transformer. Okay, maybe let's take transformer. So today we most commonly use the transformer for our analysis. So I can add those factors to the table, and I can see that with this particular harmonics flowing in the network, losses in the transformer are only about 3% bigger than normally. So basically this FHL factor is 1.03. So in order to calculate losses in the transformer, I will take losses which are created by 50 Hz current, and I will multiply by 1.03. So this will add 3%, so not too much. Stray losses are even more affected, even less affected by the harmonics, and only by 0.2%. However, if I don't have filters in the network, for example, I don't have active filter or reactive filter, and I have capacitors connected, let's calculate harmonics now, and I have that huge harmonic current, so like 18%. So now my transformer will be much more affected by the harmonic. I can see that now losses in the transformer are more than 4 times bigger than without the harmonics. So these are eddy current losses. And the stray current losses are about 22% bigger. So this is the idea. This can give you the idea of how much harmonics affect losses in transformer. So the more the harmonics you have, the bigger are the losses, the bigger is the temperature at which transformer is working, and of course this causes problems to insulation, and these problems with insulation finally will give like short circuit, possibility for short circuit, and the transformer can be simply damaged. One more example is how the report about the harmonics should look like, and this is the report for his example report actually regarding the harmonics mitigation for one of our clients, and this report covers several things. So first of all, its introduction part. In the introduction part you have an explanation. We provide explanation for our clients why you need to reduce harmonics, what are the problems, why the study is made. So it's just simple introductory information for the client who will read the report. Then the next thing we do is we provide the object description. So we provide the single line diagram and information about the network. So for example, what are the major harmonic sources, like in this case there are 2 variable frequency drives of different power, 160 kilowatts, some information about those variable frequency drives, and also other information about like measured harmonics. You can see that client measured that harmonics in his network are equivalent, like 5th harmonic is 28%, 7th harmonic is 10%, 11th 6%, and so on. So these are measurement of the harmonics in existing network, so like current situation description. Then we compare these harmonic values with existing standards like IEEE 519 standard, and we make like information for the client whether those harmonics currently exceed the permissible limits or not, and whether solutions to the harmonic problems should be made. So if yes, so we explain why, and then we start the other part of the report, so is harmonic filter selection. Here we explain what are the possible types of harmonic filters. So as I have mentioned today, it's active, passive tuned filters and passive detuned filters. Here's the explanation about each filter provided, and basically then we provide calculation reports exported from our software, and these calculation results, as you can see, are provided with detuned harmonic filters and without the detuned harmonic filters. So here is the existing network without the reactive power compensation. Here is the existing network with the power compensation, so you can see that we have resonance for fifth harmonic. And then next result is network with detuned filters with impedance of bigger than 5%. You can see that this detuned filter actually solves the harmonic problems. Then one more, like this was the last example because it solved the problem. We explained that the recommended solution to the harmonic problem is the tuned harmonic filter, and this allows to reduce all the harmonics to reach permissible limits. Then we check also passive filters and what results can be reached with using passive filters. So again, what is the recommended size of the passive filter and what are the problems. Then active filter, but in this case I think that we recommended 100 amps active filter as possible option, but finally because of high price our client used simple detuned filters. And of course conclusions to summarize all the findings in the network. And finally we provide a single line diagram exported from the our software, so you can see how the single line diagram can look like. So we have this medium voltage network where our client network is connected. We have a transformer reducing voltage from 10 kilovolts to 400 volts, and we have electrical network of the client constructed of nonlinear loads, variable frequency drives which are connected to 3 reactors in order to reduce unsymmetry of voltage, and another type of equipment. And this data can be used for calculating the filters. So basically here the example you see is the real project from our customer. So what you can do with our software is actually represented by this report. Using the software you can solve power quality issues in electrical network of your clients. You can give reliable results on harmonic and other calculations. So this would be the end of my today's presentation. So before finishing, let me check also other questions. So I would like to concentrate more on technical questions. So there are some commercial questions. So for commercial questions, you can directly ask to info@energyadvice.lt. Document. The question by Kumar was, do we have a document format for harmonics calculations? And if any case studies. So I think this example report after some time will be shown on LinkedIn site, so you can follow our LinkedIn profile and we will provide this report as an example, or maybe it's already provided, I'm not sure about that. There was also one more question, whether it is possible to analyze electromagnetical transient studies. So definitely yes, you can do this kind of analysis with the software, but it is not the topic of today's seminar. Then there was question who will support us with the filters. So after you will select the filter, so you should contact the manufacturer of the filter. So there are quite a lot of manufacturers nowadays. So basically it's not a problem when you just select the filter, you just send the request and manufacturers will definitely provide you the required filters. Then there was question how to size capacitor banks with tuned filters. So basically tuned filters does not affect capacitor power and you should select capacitor power according to requirements of reactive power in the network. So if you need 100 kilowatt of reactive power, so your passive filter should also be capable to generate that 100 kilowatt. Not necessary to connect 100 kilowatt as a single filter. It's also you can create it as a capacitor bank. So basically you can add more like filters and distribute all that power through these filters. So let's say I will copy parameters from this filter here, and I'll just simply reduce power of the filter. So 50 kilowatt here, let's say 30 kilowatt here, and 10 kilowatt, let's say here. So this could be in the same way as a capacitor bank. Your filter should be constructed of steps, different power steps, in order to mitigate reactive power. So total power of this filter is 80-90 kilowatt, and this is very close to required reactive power which is needed by this inverter. So reactive power should be selected according to requirements of the loads. Then there was question whether can we connect filter to 20 kilowatt and 66 kilowatt filter. So for high voltage filters you need to use different applications because capacitors might not be capable to withstand this high voltage. For example, if we have delta connected capacitors, so each capacitor will get 66 kilowatt voltage level. So you either need to use a transformer or you need to connect capacitors in series in order to reach this high voltage level. So in our software you can do this connection. Technically you have to check with the manufacturer if they will be willing to manufacture a filter at this high voltage. However, harmonic is more local problem and it is best to solve it locally. So if we create problems in industrial networks, and most of the harmonics they appear in industrial networks, so those problems should be solved in industrial networks as well. So all the networks connected to distribution network, they generate those harmonics, and each industrial network operator should solve problems inside their network in order to avoid problems in distribution network. So it is not the best idea to try to solve problems in medium voltage side. It is best to solve problems inside low voltage, where equipment is cheaper, it is easier to work in low voltage side. So from the strategic point of view, it's possible to connect filters to a medium voltage, but better not to do that if there is no necessity for that. Then how to evacuate heat from the enclosure where these filters are connected. So simply by using fans and other equipment which allows to actually evacuate the heat. So these are more mechanical questions, not related to today's topics too much. And Marcelo is saying that IEC do not have any standard for arc flash calculations, and when required is usually followed by... Yeah, so you are right that for arc flash calculations. So basically we have IEEE standards, and FPA is providing requirements for personal protection equipment. So many questions. Thank you for being so active during these trainings and asking so much interesting questions. It's very sad that it's not possible to answer all of your questions, and therefore because of that we have that PSM Academy. In PSM Academy usually we work in small groups, so not more than 10 people, so I'm capable to answer all the questions, and therefore we invite you to join PSM Academy to get more information about how to work with the harmonics, how to size filters. During Academy you will get the software also to try all the calculations by yourself. So during basically 16 hours of trainings you will be capable to provide report for your client and earn money from that. So the trainings will pay themselves quite quickly. So thank you one more time for being so active and asking the interesting questions. Today's trainings are over, and bye till the next maybe trainings about other topics using EA-PSM for electrical and also hydraulic network calculations. So bye for all of you. Thank you for participating. Have a nice day.